Okay, so I was in the middle of some vignettes yesterday, but I got a couple of questions that I thought I'd answer on the board. And now, how do I do this, Zubin? So, and, at least the last speaker. Try the light on this side? I don't believe it. Come on. You really think that's going to work? It does. Okay. So I did a little bit of decision theory yesterday, and a couple of questions afterwards provoked me wanting to respond. I had a couple of different kind of expectations of the loss function. So there was an expectation, the unconditional expectation, the frequentist one, looked like this. So no conditioning. And there, so theta is being held fixed, and the expectation is with respect to the x. So this is the probability on x given theta, if you want, but indexed by theta is probably the way the frequentists want to say it. So it's an unconditional expectation. And it's important to note that this theta is the same as this theta. That's really critical. So it's just a function of one theta, not of two different kinds of theta. It's really important. And then the Bayesian expectation was a conditional expectation. So here you might want to put a little x in there because that's being held fixed. Theta is now the random variable, and this is now a conditional expectation, conditioning on x. Let's put a big X in there so we treat it as a random quantity. Okay, so those are two different things. And so this object here is frequentist expectation. And the kind of the definition I was giving yesterday of what it means to be frequentist, at least and if you look at a paper, you're saying is there a frequentist analysis going on here, was that there was an expectation over the sample space. That's the kind of the giveaway. All right. And in particular, let's just do an example. So the loss function, the squared loss, is the one that, doesn't occur in any of the talks yesterday and today, but in lots of papers it does, of course. And so if this loss function is just, so e.g., the loss, and let's now call delta of x, that's just your statistical procedure. Let's call it theta hat for simplicity. So my notation is a little simpler. And so this might be just be theta hat minus theta squared. That would be a particular example of a loss function that you're all very familiar with. Okay, so that's a loss. This is a random quantity from a frequentist point of view, and that's a random quantity from a Bayesian point of view. They're kind of dual. And now if I'm going to do the frequentist risk, I'm going to take the expectation of this thing, where this is viewed as the random quantity, and that's treated as fixed. Okay? And so if you do that, you would write risk of theta would be the expectation of theta hat minus theta squared. That's just your mean square error. All right? And then the traditional thing to do at this point is to add and subtract a quantity. Right? And that quantity is now, again, an expectation. Let's be really clear here. All those expectations are the frequentist expectations over the sample space. Okay, so that's now just a number, and this is still random. All right, and now you can pull apart the square, and you get two pieces which are square, and you get a cross product. And the cross product vanishes because that cross products always vanish in statistics. It's called the Pythagorean theorem. And so you get this quantity here. That's called the variance. And then you get this quantity here. So this is a constant with respect to that expectation, as is this. So we just simply get theta minus expected theta hat quantity squared. And that's called the squared bias. Okay, so that's the bias variance decomposition, and that's all you've heard about that. I just want to make clear that in doing that, you're writing down these expectations with respect to theta. That's the frequentist expectation because it's over the sample space. Okay, so when you hear the words bias and variance, you're being frequentist. All right, but it's not the only thing that frequentists do. They don't just write down bias variance decompositions. It's just one of the most simple things you can do, and it's very useful. If you're working with squared error, at least, you separate things out of these two pieces, and often you can argue separately on these two pieces. That the bias, for example, might go away asymptotically. That's something you would probably desire. And you'd also like the variance perhaps to go to zero asymptotically. If you can show those two things together, you've shown consistency, i.e. that theta hat goes to theta, in this case, in mean square error. And that's what we mean by consistency in this particular setting. I'm going to talk a fair amount about consistency today. In general, consistency just means as the number of data points gets large, you converge to the right answer. Okay? That's what we're going to mean by consistency. And so one way, and the simplest kind of parametric setting to do that is to, if you're working with squared loss, to look at the bias and variance separately. Okay, was there any more questions on that? What E sub theta means? It's the frequentist expectation. You're looking at other sample points than the one you got. It's not a Bayesian thing to do. The Bayesian just wants to focus on this fixed x that they got. Okay, I think that was the only other thing that I wanted to say that I didn't say yesterday. So this was, let me just now cut through some of these slides and remind myself of where I was. So we were talking about F divergences in experimental design and surrogate losses. And this was the first of, I think, 4 little vignettes in frequentist analysis. So the goal here is to show you, here's a kind of a data analysis problem. Here's a fancy machine learning style algorithm of some kind. You can now try it on a bunch of data sets, and that's great, it works fine and all that, but the whole goal here is to say, what does it mean to do some analysis of this? Let's in particular, frequentist analysis. Let's convince yourselves that it's actually a good method in some sense, not just that it works well on data sets or that it's clever. Okay, so I'm going to try to show you how that kind of thing is carried out in a bunch of little vignettes. Okay, so this first one had to do with the experimental design problem, where we were interested in developing a quantizer as well as a discriminant function jointly. So we kind of had that kind of set up where we had x's which are available in the environment in principle. You can measure them, but you don't use them centrally. So it's a distributed classification problem where you first of all quantize each of the x's by an experimental design or a quantizer q, and then the z's are small numbers of bits, and you transmit them to a central site where you can then do the quantization, the discrimination, which is the function gamma. Okay, so this is kind of an example of probably, I think, an emerging field of distributed machine learning. Where you don't want to send all the data back to a central site. You want to locally quantize or do some other kind of compression and then send a small bit rate back to a central site where you do something sophisticated. So how can we solve that problem in a theoretically satisfying way? So I kind of set up this problem where the risk function was the probability of error, where the label was different than the one you predicted. And the decision now has got 2 parts to it. It's both the experimental design or quantizer and its discriminant function. And we want to find the discriminant function and quantizer that minimize the probability of error. Okay. And then I talked about kind of the literature. There's been 2 main literatures that focused on half the problem but not on the whole problem. Either you assume Q is known and try to find the discriminant. That's kind of machine learning, statistics. Signal processing assumes that all the probabilities are known, so you could actually get the discriminant just by Bayes' rule. But they focus on getting Q. And once you get Q, then you do actually use Bayes' rule together with a quantizer. Okay, and so the signal processing literature focused on these things known as F divergences, because more or less as a heuristic. You want to push distributions apart, and these are measures of how close distributions are. And so if you maximize these divergences, you're pushing them apart, and that's a way to get a principle of how to choose the quantizer or the experimental design in general. Okay, so there's just a list of some of them. There are many of them. Any convex function of the likelihood ratio averaged defines an F divergence. And then there was a theorem due to Blackwell that sort of said that F divergence is going to be used to rank procedures in terms of risk, i.e. probability of error, for some unknown prior. And so that motivated people to look in that literature to look at F divergences. And then the machine learning perspective was to have a decision theoretic story where you develop these surrogate loss functions. And there they are for like boosting, support vector machine, logistic regression, and so on. They are upper bounds on this intractable 0-1 loss. And then there's a theory that says that if you basically have your surrogate loss is differentiable at 0 and has a strictly negative derivative at the origin, then that's necessary and sufficient for Bayes consistency. So I didn't actually define Bayes consistency yesterday, but it means what you expect to mean. It means as the number of data points gets large, that you converge to making the probability of error goes to 0, or sort of the Bayes rate, the best you can do. Okay? So in this case, it's a functional estimation problem. It's not just a parameter estimation problem. Okay, and so I think we're getting close to where I stopped yesterday. So we're trying to define this notion of universal equivalence among surrogate loss functions. And I had a little notation. At the end of the day, the main piece of notation is that for a given surrogate loss function, so not 0-1 loss in general, but maybe, we have an argument which is the theta. So this is a frequentist risk. And just expanding it out, you get probability under y equals 1 and probability under y is equal to -1, and then we still are doing the averaging with respect to the z. So because we have that expectation is an expectation over both y and z. The data has a y and a z component. It's a classification problem. So we did one of the averages and not the other, and that's what the risk looks like. Okay, and then we profile. We do this frequentist sort of, well, it's not a frequentist thing, it's just a thing to do, and then you try to prove as a frequentist that it's okay, that you did the right thing. So we take the infimum over the discriminant function. And so we did that for 0-1 loss, and we've turned out that the 0-1 risk, the profiled 0-1 risk, was the negative of a F divergence, in particular the variational distance. And then we did that for a bunch of other examples, and we found that there was a general story. It seemed to be emerging, which was that profiled risks of surrogate loss functions always were equal to the negative of an F divergence. Okay, so that's a new result. That's not been present in the literature for all these 40 years or something. Well, it's a new result once we prove a theorem about it. And the theorem tells you there's this many-to-one link between surrogate loss functions defined in this way, not just loss functions, but these special class of surrogate loss functions, and F divergences. And so the proof needed to define a notion of the classical notion of convex duality. And here's the first theorem, which we went through yesterday, which is a theorem going in one direction. Given a loss, you can get an F divergence. That was easy. And then backwards, given an F divergence, you can get a whole family of loss functions. And that family was parameterized, here it is, by a free degree of freedom, this function F, that has to be just simply increasing, continuous, and convex. Okay, so here were some examples of different choices of G that gives you a bunch of different loss functions, all of which lead to the Hellinger distance. And then you do this just by doing the conjugate duality calculation. And here's a bunch of F or G functions that lead to loss functions that include the hinge loss, all of which yield variational distance, and then KL divergence. Okay, and so here was our problem then we're going to try to solve, which is that we're going to try to get Bayes consistency for choosing both the quantizer and the discriminant function. And now I'm going to draw another picture again like I did yesterday. So here's the world of losses, surrogate losses, so these special kind of losses. And then F divergences. And we've got this characterization theorem that says there's for every F divergence there's a region over here that corresponds. Okay, and so the theorem, the more now statistical, that's kind of just a bit of convex analysis really. The statistical theorem now says that what you need to do is to start with 0-1 loss. So here's a particular 0-1 loss. It lives in one of these regions. And go over to the corresponding F divergence. And now take an expansion of that given by, so there's the variational distance min of U1. That is the F function that gives you variational distance. Get the little pointer here. So there's a little F function right there. And now take kind of this affine expansion of it right here and define a new family of divergences where these are the Fs. So this is kind of a little class that's kind of expanded around the variational distance. And now go backwards and find all of the, bundle up all of the loss functions that map into that little expanded region. Okay? All right, and so that gives us a set of losses. And those are going to be, it's a characterization theorem. So those are the ones that give you Bayes consistency, and they're the only ones that give you Bayes consistency. Okay, so this is a characterization of consistency for both joint estimation. All right. Okay, and so now this little part of the story right now is just kind of some standard function space consistency arguments. There's nothing really new here. This is what you do in empirical process theory, aka statistical learning theory. And so I'm going to kind of skip through these slides a little bit quickly. It's just a bunch of notation that sets up something that you hit it with a standard hammer and things go to zero. And I'll just point out what's new here that's not present in the usual literature. Okay, so first of all, so here's our sort of our risk function, and now empirical. So it's over the data. So yi and z and xi are the data, and then we use our quantizer to map that into z, and we average over z. That's going to be our risk function, and then we average that over the data. And now let's suppose there's an oracle that can solve that optimization problem exactly. Now we have this increasing compact function classes, so there's the quantizer, this ultimate one here, which is really rich. It's got all kind of maybe all possible measurable functions, and then this C increases slowly to that. And similarly, look at the set of quantizers that we want to look at in the limit, and then D these are called sieves. So these sieves increase up to both gamma and to Q. All right, and so for a given one along the way, you have this optimization problem to solve. This is kind of just it's called sieves. And so you'll assume we can solve that exactly. We're doing theory now. There's an oracle that can solve that optimization problem. We call that the answer the oracle returns. And then let's call this one particular solution. All right, now the best you can possibly do is to optimize the Bayes risk, where Bayes really means 0, 1. That's what we're focusing on here. So when I say R sub Bayes, I mean the risk based on 0, 1 loss. And let's call this number here the best you can do using if you'd had the true Bayes risk. So that's called the Bayes risk. All right, and so the excess Bayes risk is the risk that we have on our optimized solution, which is based on the data minus the best you can do. And we want to drive that to 0. Okay, and the way you do that is you separate, just like you did with bias variance, you separate this into an approximation error like the bias and an estimation error like the variance. And this is just Pythagorean theorem really in function space. So you kind of just separate these two pieces, and the sum of them is the original risk. So let's not get into the notation there. And once you do that, you get the approximation and estimation error appearing here. And this excess risk is upper bounded by those errors, all right, plus another term, which has this m sub n here. This is a quantity that depends on your particular loss function and depends on your choice of sieve. And this quantity, it needs to be finite, bounded. And for all the usual loss functions and all the usual kind of sieves like kernel classes, this is bounded. It's not hard to show, and so let's not worry about that too much. And then you have a square root of log of the error, delta, divided by n. So it's 1 over square root of n kind of convergence. Sending the approximation and estimation error to 0 is the usual story of all the kind of non-parametric classification kind of things. So there's nothing new there. You just choose your sieves appropriately so these can be driven to 0. They kind of grow at the right rate. That's all you have to do. All right, and the new term is here. Now, we prove this theorem under the class of phi obtained in this way. Okay? All right, so this kind of justifies our choice that I expanded the F divergences in this way and then went backwards to the phi, because we get Bayes consistency for everything in this class. That's what the theorem is stating. That's kind of the key issue. Everything else is kind of technical, is that this class all leads to Bayes consistency. Okay. All right, so that's a statistical theorem. But now we're going to say something stronger, which is that this leads to a notion of universal equivalence between loss functions, and it's going to lead us to necessary conditions, that only that class gives you Bayes consistency. Okay, so this is going back to Blackwell, really. This is kind of Blackwell's idea, but done more broadly for all surrogate loss functions, which those didn't exist in that day, but we now have them, and leads to a nice general theory. So consider two loss functions, phi1 and phi2. We know that they can be mapped into F divergences, and let's call those F1 and F2. And now let's define phi1 and phi2 to be universally equivalent, denote it this way, if for any joint distribution on the x's and y's, i.e. completely non-parametrically, and whatever quantization rules you want to choose, whenever the profiled risk under the phi1 loss ranks QA as better than QB, then it is also true that the phi2 loss ranks QA as better than QB under the profiled risk, if and only if. So that looks like kind of an equivalent statement, that if this phi1 loss is ranking things in some way, the phi2 loss does as well. They're equivalent from the point of view of ranking quantizers, which is our goal in this problem. Okay, so that needs to be done for any probability distribution. That's why we would call it universally equivalent. Okay, so that's just a definition of an equivalence notion. It has nothing to do with F divergences at this point. It's just a definition on the loss side of the board. Okay, so it's kind of borrowed from Blackwell, and the economists used ideas like this a lot. Basically, they borrowed from Blackwell as well. Okay, but now given that definition, there's a theorem which does relate to F divergences, which says that you have universal equivalence in the sense just defined if and only if the F divergence corresponding to phi1 is related to the F divergence corresponding to phi2 according to that little affine expansion. So because that's an if and only if statement, that characterizes equivalence among loss functions, which seem to have nothing to do with f-divergences, in terms of a very simple property of f-divergences. So if you're just interested in loss functions, this theorem tells you should also be interested in, if you're interested in losses, you should also be interested in f-divergences, because you can learn a lot about loss functions by looking at f-divergences, and vice versa. Okay. So one direction of this is very easy, and the other direction is the core of our paper. It's several pages of proof, so it's a little challenging. All right, so that's the last theorem in this section of the talk. And so I won't tell you how you prove it and so on, but let's just assume it's true. All right, and now let's just read off some easy consequences of that. Okay. So suppose we started with 0, 1 loss here. We mapped over, and we expanded, and we mapped back. And now we get a whole bundle of loss functions there. They're all universally equivalent by our theorem to 0, 1 loss. All right, what's that mean? Well, that's good. Those are loss functions under any probability distribution which will rank quantizers the same as 0, 1 loss ranks them. Well, 0, 1 loss is our goal here. That's the overall loss function we're trying to optimize. So if you're ranking the same as 0, 1 loss, you're consistent. You're doing the right thing. Okay? All right, but this is an if and only if theorem, which also says that if you're not consistent to 0, 1 loss, if you're not equivalent to 0, 1 loss, if you're outside here, if you're another loss sitting out there, all right, that means you're not universally equivalent to 0, 1 loss. That means there exists some probability distribution on which you give a different answer than 0, 1 loss, which means you're not consistent. Okay? There might be some probability distributions in which you give the same answer, right? But that's not good enough for us. We're trying to prove a general theorem, which is that you're the same in general. Okay, so this reduces to a very simple problem now. What loss functions are universally equivalent to 0, 1 loss? All right, well, that's easy, because we know how we go over to f-divergence space. 0, 1 loss leads to variational distance. You expand out variational distance, and you come back, and you get a whole class of loss functions. All right? In particular, you get the hinge loss as one of them. Hinge loss is universally equivalent to 0, 1. So hinge loss, i.e. the support vector machine, leads to consistency. You can use the support vector machine formalism and jointly optimize it with respect to the discriminant, which is what's usually done in the support vector machine, and a quantizer. And if you then handle all the sieves kind of correctly, then that will give the right answer. Boosting is not. All right? Boosting leads to another f-divergence, which is not in this family. So if you use the exponential loss behind boosting, then you're not equivalent, you're not consistent. Okay? You can't use that function to learn both of them in general. And there might be special cases in which it would work, but not in general. Okay, so that's an interesting characterization that, boosting, SVM, all these different losses in the standard classification are all consistent. They lead to, that's one of the earlier theorem we talked about. But when we do this harder problem of doing the experimental design and the classification, some of them are and some of them aren't. Yeah.
What about the absolute loss function and square loss function? And you mentioned something.
Yeah, the absolute loss function is also universally equivalent to 0, 1 loss. And the square loss, if you take the one that comes down and then is flat after that, is also. And I don't have a kind of a list of all the others. It's sort of, in fact, I don't think none of us have ever really done that, kind of looking at the others at this point. I don't think it is, actually. But haven't sat down and worked that out. You just got to, it's easy to work out. You just calculate the f and you see if you can get it by is it affine related to the original one? I don't think it is. Okay, so that's that story. All right, and so next little application of this. So that's one application as to kind of these consistency results. And you can use this for other kind of problems now. That was for quantization and experimental design, but you can also use it for feature selection. That's another kind of experimental design problem of how do you find a feature selection stage together with a classifier, discriminant, that they jointly estimated together give you consistency. So you can use this for, it hasn't been done, but that's something that would be fun to do. Here's another class of applications of this, which has to do with the estimation of divergences. So, take the Kullback-Leibler divergence. We might like to estimate a Kullback-Leibler divergence from data. Now, why would we want to do that? Well, lots of reasons. Sometimes people want to optimize KL divergences. So you'd probably need to be able to estimate it if you expect to be able to optimize it. Special case of KL divergence is the entropy. And a lot of people are interested in estimating entropy from data. Okay? So there's, for example, the KL divergence. How might we estimate that from data? Well, KL divergence is based on two measures, P and Q. You'd have to assume you can get data from both P and Q. And then in some sense, would want to plug it into this formula and get some kind of an estimator. And the problem here is that, look at the P part. You've got both P and log P appearing together in the formula. And so if you think about things like kernel density estimation, you'd have to develop a good bandwidth for estimating the P part, but also the log P. And those are incommensurate things to do. All right? And so this is actually a hard problem. This is an open problem still in the literature, is trying to estimate these kind of divergences. All right? So in fact, there is a lot of work on this. Some famous statisticians have worked on this. If you're working with one density, KL is a function of two densities, so it's a little harder. And this is really not really a closed problem. There's not actually that much work on it, and there should be more. Okay, so a fact about the line of work. In the line of work I talked about, you get a variational representation of these divergences. That's kind of not that hard to see. Here's a general way to express it. This is probably more formal than I needed to be, but you can show that these divergences in general with any phi function, these Ali-Silvi divergences, are equal to, under a certain condition, in general greater than or equal to, a particular variational expression. It's a supremum over some function class of an integral under one measure of f, and then an integral under the other measure of the conjugate dual function of your loss, phi. Okay? If the intersection of this function class f with this subgradient of phi evaluated at the likelihood ratio is non-null, which is pretty typically be the case, then you get equality here. All right, so that's a little exercise. It's just a little exercise in variational calculus if you want to verify that. I think what I'm going to do instead of having you verify that is to look at the special case of the KL divergence, where you plug into that formula the logarithm minus 1, which leads to the KL divergence, and then do the conjugate dual calculations, all very easy, 2 lines of calculus, and you get this representation of the KL divergence. So this is exact, this is equal. So this is the exact representation of the KL divergence. And if that's not obvious to you, just simply do this supremum. Just take derivative with respect to g, functional derivative, set equal to 0, and solve, and you get the KL divergence. Okay, so that's kind of interesting that you can represent the KL divergence in a variational way. And now, of course, you see that the problem has a log g and a g in it. That that kind of two scalings are present in the problem. But this leads to kind of a nice little. It has these two pieces here. If you got data under p, you could make this integral be the empirical integral under p, and then the data under q would lead to an empirical integral here, i.e., you'd get sums. And now you'd like to optimize that over some sufficiently rich function class. Right? And that would lead to an estimation procedure for KL divergence. All right, so that's what we propose to do. So replace the integrals with empirical expectations. And here they are. So I wrote that as an empirical expectation. It really just reduces to a sum over the data of log g. That's all that means. And similarly with q. And there you go. There's an optimization function that you could optimize over some function class. For example, kernel classes would be a typical thing to do. And then the optimum is g hat, which is an estimate of the likelihood ratio. And you could plug that into your KL divergence. Okay, so that's an interesting estimator. It wouldn't surprise us since we're working in rich function classes that we would need to regularize, and so in fact we do need to regularize. So let's now look at our function class g and develop some measure of complexity for the functions in that function class. Let's call that I of g. And let's now do a sieve kind of procedure where we look at highly regularized g's, and then we take the union of, let g be kind of a union of a nesting of these. Doesn't have to be nested, but let's let it be nested for simplicity. So it's all those classes in which this functional, which is typically monotone, is less than or equal to some constant. That constant grows and goes all the way up to script g. So then our estimation procedure is a regularized estimation problem. You take the original functional here, and you add a regularization penalty, and you take the minimum over your function class. Yeah?
Can you comment, is there a relationship between this sieve approach and structural risk minimization?
I think structural minimization is just sieve approach. I think it was a new word given to an old idea. Or, you know, I don't know historically who came first. I wouldn't want to argue about that, but really it's just the same. Okay, so there's a functional to optimize, and now, you know, we have a cute little idea, and we could try it on data. It does work. In fact, I'll show you some plots of it working. In fact, it may be state of the art for this problem, but I'd like to say that this really does work. I can prove something about it. That's kind of the point of this lecture. So can we prove something about it? And the answer is yes, you can. So here's a theorem that shows if you take that regularization parameter to vanish sufficiently slowly at going as n to the minus 2 over 2 plus gamma, then under the true data generating distribution, the Hellinger distance between the truth and your estimate goes to 0 at this rate. Okay, so actually so now we're not just giving consistency result, we're giving a stronger kind of result that we actually get a rate of convergence. And now I can compare it to other procedures which are also consistent and see if I get a better or worse rate. Okay, and in fact, the literature on this has lots of rates floating around, so if you want to compete, you better get your rate on your method. All right, so there it is. We also can actually say something about how the complexity functional goes to converges as well. Okay, so that was a theorem. I'm not going to give you any idea how that was proved, but if you know the word, I'll just tell you one pointer, which is Sarah Vandegeer has a great book on M estimation. M estimation just means empirical risk minimization or other kinds of estimators. Uses empirical process theory, and it's just a full book on the kind of techniques you need to use to prove that kind of theorem. So if you want to really get a good theoretician's book on these kind of things, it's a little book on M estimations. It's a great book. Okay, so what about some empirical results? Does this work in practice? All right, so here's just some examples. So this is the KL divergence between a beta distribution and a uniform distribution. This is a function of the number of data points. And the state-of-the-art method is something due to Wang, Kulkarni, and Verdu in the information theory literature. Here's a couple of examples of their algorithm. They have a free parameter which you have to choose in a certain way, so we chose it in a couple of different ways. This is kind of a multivariate histogram-y kind of procedure. It's pretty complicated to implement. In one dimension it's easy, in multi-dimensions it's hard. But it's something they have a proofs for, and it is a pretty effective method. So it's widely used. And here's the rates empirical on these data for this, it's artificial data generated from these things. And so it's converging to the right answer, but not as fast as our new methods. So these are our methods for a couple of different choices of the regularization parameter, converging quite a bit faster. And this is for this is KL divergence of a mixture against a uniform. And again, we're beating the current state of the art. And then we did this for a whole bunch of other different KLs between different classes of distributions. And there's a couple of cases where we do the same roughly. I guess here you might sort of say we're doing the same. But overall, the picture is pretty good. This seems to be the state-of-the-art method. Okay, so that's a summary of vignette number 1. F divergences and surrogate loss functions turn out to be closely related. And I always like this kind of result because I'm getting old and my brain can't hold all kinds of different ideas. And so if you can unify things for me and show that F divergences and surrogate loss are very closely related, that's great. I don't have to remember one kind of thing. And I would encourage people to think about using this for other applications. We just use it for a couple of small applications, but it's a really general framework, and I think it's got a lot of promise for all kinds of experimental design and estimation problems. Let me pause for a second. Any questions about that? That's vignette number 1, and there are going to be hopefully up to 4 of them, depending on how much time I have. Yeah?
I'm not sure if you mentioned this, but what is the loss function that corresponds to the KL divergence?
KL divergence, so what is the loss function corresponding to the KL divergence? Good question. Okay, I don't have it at the top of my brain. I have to do the calculation. But if I were you, I'd just sort of take out a pen and paper. It's not hard to do it, but I just can't remember what it is off the top of my head. Any other questions? Okay, so let's quit that talk. And, oops, what am I doing? Okay, and let's go to talk number 2. I need to find it. That should be it right there. Okay, good. Okay, so I couldn't talk about frequentist analysis without talking about where people's main interests are these days, and it's this area of high-dimensional analysis where the number of data points is getting large, but also the number of parameters is getting large. So classical asymptotics and classical theory was all about the number of parameters staying fixed, the number of data points getting large. Very, very useful still, but very classical. That's not what people are mainly publishing these days. They're publishing these other kind of results. So I'm going to mention a couple of ideas that have to do with, again, here's an algorithm. It's kind of cute. It's got kind of serious optimization ideas behind it, but can we prove something about it working? And we're going to do this in the domain where the number of parameters, quote unquote, is growing. So non-parametrics. Okay. Okay, so as I just noted, kind of classical asymptotic theory was mainly focused on this problem, parametric problems. And there are lots and lots of applications where this setting is just not appropriate. The number of parameters is often growing at the same rate as n, or in many applications, the number of parameters is larger than n. And in a classical theory, that would be kind of impossible to get consistent procedures. You need the number of data points to go faster than p. But if you have some notion of lower effective dimensionality, then it may be that you don't need this constraint and you can still get consistency. And that's what many people have been investigating. The main notion of low effective dimensionality is sparseness. Okay, so in particular, this is the kind of one that there's been sort of huge numbers of very strong results on, which is just sparse linear regression. We have just classical linear regression. We have univariate observations. They're n subsaturate observations. They're obtained by x times beta star. And there's some subset of the beta star vector which is non-zero, and then the other set is assumed to be 0, where the number of non-zero interests is much smaller than the total number. And there's noise. And you would like to be able to hopefully recover just the non-zero set and set these exactly to 0. Okay, so there's many, many applications of these things. Sparse compression, sparse regression, and so on. One kind of class of applications that's increasingly popular is a frequentist approach to graphical model selection. So this is an alternative to the Bayesian marginal likelihood conjugate priors kind of thing that you're familiar with, which is you simply treat each node in the graph as a regression on its neighborhood, and you use sparse regression techniques to try to zero out as many coefficients as possible. When you get a 0 coefficient, that removes an edge from the graph. Okay, so increasing work on this sort of thing. So if you assume that there is a sparse graph, you would like to be able to say that I can recover that sparse graph. Another example of this is sparse principal component analysis. So in general, the eigenvector of a covariance matrix is not necessarily sparse. It's pointing in some arbitrary direction. But if we have big P, small n problems, we would still maybe hope to estimate an eigenvector if it's actually the case that eigenvectors have many, many 0 components. And so how could we do that? Okay, so the general problem then is going to be decision theoretic, frequentist. We're going to have some fixed loss function, and we're going to have some notion of error. And we'd like to see, can we achieve that error? Can we get a rate, basically? For what sample sizes do we achieve that error? I get a rate. And we'd also like to say something about computation. So, classical statisticians didn't say anything about computation. They assumed that you just did whatever computation you needed. But it's increasingly the case that we want to think about the computation side. So we might be able to say, here's a procedure which has a certain statistical rate. What's its computational rate? And can I trade off the computational rate against the statistical rate? In particular, we're going to talk about comparing between quadratic programs and second-order cone programs. We know their computational rates, and we also like to get a statistical rate and see if it's worth paying the extra computational cost for the extra statistical efficiency. Okay, so we're going to do 2 examples of this. Multivariate regression in high dimensions. So high dimensions is the key here. And multivariate regressions doesn't mean that x is a vector. It means that y is a vector. Okay, so for every covariate x, i.e. input x, you're going to have a vector of outputs, a vector of responses. That's multivariate regression. Okay, and we're going to formulate this problem as a second-order cone problem, an SOCP. And we're going to compare that to the lasso, which is just L1 shrinkage, L1 regression, done independently on every one of the response components, and see if we can get any benefits from the SOCP, which costs us more computationally. And we'll also compare a couple of different procedures, again, a cheap method and then a computationally more expensive method, and see if we can get a difference in rates here. Okay, so this is just kind of the classical setup of the lasso, many other kind of procedures, Danzig selector, and so on and so forth. Again, it's just univariate regression. There's a design matrix. There's a parameter vector, noise, perhaps. So the usual way to approach this is a regularized least squares problem, quadratic program. So you have a squared error term, and then you have a regularizer. L2 regularizer is called ridge regression. L1 is L1. L0 is just a count of the number of components which are non-zero. That leads to an NP-hard problem. And then there's also attempts to look at sort of non-convex problems where the exponent is between 0 and 1. But I'd say that L1 has been the focus of most all the attention because there's surprisingly strong results available for L1. It acts kind of like L0 in certain situations. Now, there's a huge literature on this, and it's important to kind of divide up the literature into what the goals are. And the goals are all decision theoretic, but there's different choices of loss functions. All right, so some people are interested in squared error. This is regression, after all. That wouldn't be too surprising. But they're interested in squared error for the predictions, all right, not for the parameter estimates. Okay, so you might use a plug-in or something, but you get a parameter estimate, you plug that in, you make a prediction, and you compare that to the new data which you might get, and you take your loss to be an expected error. Okay, so that's a loss function, even though it has an expectation there. You would now look at that loss over multiple repeated data sets, and that would be the frequentist risk you would be calculating there. Okay, so that's prediction. A lot of people have been looking at that. The more classical thing to do is just look at the squared error in terms of parameter estimates. So if you really care about the parameters, which you do in many situations, you might care about that. The one we'll focus on is what's called support recovery, which is just the indices in which you have non-zero parameter values. Okay, so I'm going to make an estimate, and some of those slots, some of those indices will have non-zero values, and I'll return the support as my estimate. After I've done that, I could then do parameter estimates just restricted to my support, and that would be a way to actually do parameter estimation as a two-stage procedure. Okay, so you'd like to, your risk now will be the probability that you don't get the right support. Okay, so it's a different risk function than the one in the first two cases. Okay, all right, so now let's talk about this multivariate regression problem. Okay, so a little bit different. So now the Y is a matrix. So they're n data points, but every row of this thing is a whole vector. Okay, so for every x, you get a, every x row here, you get a y row as well. So it's x, y pairs where both are vectors. Okay. Therefore, the B is no longer a vector. The B is a whole matrix. All right, and so you can think of each column of this thing as all the coefficients appropriate to one of the y components. Okay. Okay, now you might hope to be able to do good regression in this situation when these regressions have something to do with each other, related regressions. So regression for component y1 might be related to the one for y2. In particular, they might share their supports. I.e., there might be some relevant features, relevant x's, which are relevant across multiple regressions. And you might get more power by doing the regression simultaneously in that situation. Right? So that's the intuition. And you could now go in a sort of in a Bayesian story. If I put on a Bayesian hat, I would kind of have a hierarchical Bayesian model of some kind to try to capture that. We're not going to do that in this talk. We're going to be frequentists, so we're going to have to develop some kind of loss function which captures that. Okay? We're going to try to do some sort of shrinkage of parameters which we hope might be related towards each other, and not just shrinkage of everything towards zero or towards a mean, which is what the lasso would do. Okay, so we're going to have design matrix, matrix of observations, and we're going to look at all these parameters going to infinity and try to say something theoretical about this situation. Okay, so our first bit of work on this is Guillaume Obazinski, Guillaume's work. Started with block regularization and second order cone problems. Okay, so here's going to be our regularization problem. We've got y minus xb, just like in classical regression, and we're going to add that up over all of the columns, or rows, however you want to think about it, of this difference, of this matrix difference. So we'll take the Frobenius norm. We'll just add them all up. Okay, so it's the total squared error over the entire matrix of observations now. Okay, so that's just the usual squared loss. Okay, now we need a regularization of some kind. And as I alluded to, we're going to try to find a structured regularization that groups coefficients together. Okay? All right, in particular, what we're going to do is we're going to take a sum over all the different coefficients. There's p of them. And we're going to look at the ith row of this matrix. Okay? And we'll take the Q norm in that ith row. So in particular, Q for our work is going to be equal to 2. So we're taking the 2 norm for a row of coefficients. Now, what is a row of coefficients? Right, that's all the coefficients which are associated with the same x component. Okay? So if that x component is useful across multiple regressions, all those coefficients might be not non-zero. And we'll bundle all of them up by taking their squared norm. All right, now, we don't believe that many coefficients are useful. Hopefully, this is sparse. So now we'll take an L1 sum of those L2 norms. Okay, so that's going to hope that will drive many of those L2 norms to 0. When you drive an L2 norm to 0, drive all the coefficients to 0 in that entire row. So this tries to zero out entire rows of this coefficient matrix, not just individual elements of a vector. Right, but otherwise, it's basically the spirit of the lasso. Okay, so that's going to be our regularization. It's a block norm. It's an L1, L2 thing. And there's been a lot of work on various forms of this where Q is equal to infinity. There's been work on that by Turlock et al. Setting it equal to 1 is not useful because then you just get an L1, L1. It just becomes a total big L1, and there's no structure. You've lost all your hierarchical structure because you wouldn't want to do that. That would be just independent lasso. But there's these other possibilities. Okay, so there's a lot of work on related ideas. Okay, so the two strategies for trying to recover the support. One is you could do separate lassos on each of the coefficients, or each of the regressions, and get a coefficient vector, and then make the row support sort of the union of every place that you have a non-zero coefficient. You take the support to be the union of all those. And the other one is that you solve the problem I just had on the previous page. And I didn't mention on the previous page that that problem is a second-order cone problem. So this problem right here has a quadratic loss, and it has an L1, L2 penalty. You can do just a little bit of work, and that turns into what's called a second-order cone problem. I think you had a talk by Vanderbeek. So talking a little bit about convex problem. This is an example of a convex problem, which is easier to solve than an SDP, but not as easy to solve as a QP. Okay, so that's going to be our problem here, is to solve the SOCP. So more complicated and complex to this, but maybe going to be better. Okay, so subsequent work, we then proved we did some theory for this. So we tried this on problems. It does work. It's a successful way to recover coefficients in multivariate regression. But can we say something theoretical? And so here's a theorem. And I think in this part of the talk, it's sort of I'm running on a bit. There's some bunch of technicalities. I'm going to mainly just skip them. There's the paper on the website, which you can look at. But just to remind you, so we're solving this. Here's our problem we're solving. It's an optimization problem. We're trying to get the support out of that. We make some assumptions on the design matrix. You need to make assumptions on the design matrix. So the rows are taken from a sub-Gaussian distribution, and we have some conditions on the covariance. All right, and we show that if the rescaled sample size, I'll show some examples of this rescaling on some plots, but basically it's the sample size divided by a quantity, which is essentially the logarithm of the number of parameters minus the number of regressions. And then this factor right here is what we call sparsity overlap function. And it has to do with kind of how much overlap there is in that actual B matrix, in B star. If there's not any overlap in B star, if the different x's don't have, if the different regressions don't have use the same parameters, then you might this number might not be very favorable. If they have a lot of overlap, it might be favorable. So there's a number there that depends on the actual B star and also the covariance of the X matrix. Okay, so if this number is bigger than a certain threshold, i.e. if the number of data points is larger than this multiplied by a factor, then it turns out with high probability there is an exact solution to our SOCP. That's actually non-trivial because this is a highly undetermined problem, but there is a unique solution in this regime. And you get all of the rows that are larger than a certain coefficient, which is going to 0 as a function of n. So this says you actually do support recovery correctly for this large value of n. And I think I'll sort of skip this. There are just you need in all of these procedures, from lasso and all the rest of them, to say something about the design matrix X. It's usually taken to be from a random ensemble. There is literature on deterministic designs as well. And you make certain assumptions on the spectrum of this thing, that it has bounded eigenspectrum, and that there is an incoherence among the different rows of the design matrix. Okay, so let's not get into that. So this basically is an empirical result that's substantiated in the theorem, which is that for this parameter getting larger and larger and larger, beyond some point, this rescaled parameter, n divided by something, beyond some point, the probability of support recovery being correct goes to 1. Below that, it goes to 0. Okay? And this is done for a number of dimensions growing, and we see that by scaling things in this way as log of p, that basically the p dependence vanishes and we get these curves that lie on top of each other. All right, so this shows that we actually have the right rescaling. And n log p is great. All right? It says that p can grow very quickly relative to n, and you still get support recovery, exact support recovery. Okay? All right, this is for different, so angle here is the angle, this has to do with the support overlap function. So we did this under a different regimes for that choice for the particular design matrix. And what is this support overlap function? Well, what you do is you take, it's some facts about the parameter matrix. Okay, so you look at the gradient of this L1, L2 norm on B. You use that to form a gradient matrix. You normalize that, or that's equivalent to normalizing. You form a certain gram matrix where it's the gradient times that the covariance of the part of the X matrix that has non-zero coefficients. And then this function I was talking about here is the maximum eigenvalue of this matrix. Okay, so it's a quantity you can calculate in simulations, and that's what it is. Okay, so if you want to spend more time with the paper, you can we go through very special cases of calculating this and seeing how much overlap we get, and therefore how much we're dividing that scaling factor by. Okay, so I'm not going to get into this, but here's some just different exampple of choosing coefficient matrices and getting different sparsity overlaps. And so there's some favorable cases where you kind of have orthogonal situations. If you have aligned regression, where everybody has all of the columns of this gradient matrix are the same, you don't do any better than the lasso. Otherwise, you do better than the lasso. Shifting over to the left means you need fewer data points to get the same probability of support recovery being correct. And so we have simple situations in which you can get up to a factor of the number of regressions improvement. Okay, so if I have k regressions, I can actually I need k fewer data points in the most favorable situations to beat the independent lasso. Okay? We originally had thought that we will never do worse than the actual lasso, independent lasso. That turns out not to be the case. So we have some kind of somewhat pathological situations where you can do worse than independent lasso, but in general you improve. Okay, in fact, this is the statement of that kind of theorem about how much you perform relative to the ordinary QP. Under this particular situation, where the covariance matrix of that portion of the design matrix is identity, then we actually always improve over the independent lassos. But in general, that's not the case. Okay. All right. The next few pages are proof sketch, and I put them in the slides. I'm not going to cover them, but this was meant to kind of be a theory talk. So if you want to look through these slides, you'll sort of see the techniques that are being used here. It kind of is convex optimization meets sort of concentration inequalities. That's really what's happening here. Kind of Gaussian concentration inequalities. So there's some kind of projection arguments, and at the end of the day, you use large deviations to establish some kind of a rate, and then you bring that into the optimization story, and blah blah blah. Put it all together. So let's skip all that. Okay, so let me just briefly again, I'm kind of running through a little of this just to give you a little flavor of kind of these ideas. There's a large literature also on sparse PCA. So if we want to do PCA, but we make assumptions on the sparsity of the eigenvectors, maybe we can do PCA in really high dimensional spaces and do it provably. Okay, so a lot of people have been working on this. In general, if you don't have any sparsity assumptions, you can't do it. There's kind of classical results on that. But if you have structured ensembles like sparse eigenvectors or sparse covariance matrices, then you can actually get consistency even though P over N is going to infinity. It's seemingly impossible, but it's true under these kind of conditions. All right, so one of the theoretical situations where this is studied is what are called spiked population covariance matrices, where your covariance matrix is a sum of rank 1 matrices. So these are the leading eigenvectors, plus some other matrix, typically the identity matrix. All right, and then you look at different kind of sparsity models. Either you have hard sparsity where these eigenvectors have exactly k non-zero coefficients, or you have some softer versions of that, and you study these things theoretically. Okay, so we have a project where we were interested in doing sparse PCA using kind of sophisticated optimization tools, in particular the SDP. And this is kind of a pretty straightforward relaxation. Again, if you saw a talk on convex optimization, you would probably know how to do this. You remember that the eigenvalues, according to the Courant-Fisher variational principle, are gotten by maximizing over the ball of this Rayleigh kind of coefficient. And you can rewrite that problem using as a semi-definite program, just using a linear expression, this trace of ZQ. And you do that over all positive definite Z that have unit trace. Okay, so that you maybe now know how to go from there to there after the lecture the other day. Okay, so you can use this idea now then to relax the sparse PCA. So there's the same component just pulled down into there. All right, and then we want to do sparse PCA. So we add an L1 norm to the objective function, and now we optimize that, and this is still a semi-definite program. Okay. Okay, and now Arash Amini and Martin Wainwright have proved a theorem about this, that they have the same kind of class of theorem that we talked about for the other situation, which is that you actually do recover under, this is a simple example of just a rank 1. There's one eigenvector and then identity, one large eigenvector and then identity spiked covariance matrix. That you get exact recovery, here's the rate under that situation using the SDP. Okay, so that was an interesting theoretical result on that. And there are some known results on thresholding estimators, which achieve slower rates. If Q is equal to 0, it's the same rate as before, but it's slower for Q not equal to 0. So if you have, this is just for the first eigenvector, but if you have well-separate eigenvalues, you get this for the first eigenvector and the whole, this is for general matrices. We have well-separated eigenvalues. And that's for just a particular kind of estimator, the thresholding estimator. There's also minimax rates known. So one of the things frequentists do a lot is they don't just try to show that certain methods are good, they also want a notion of optimality. They try to show that there's the best possible rate you could get, the minimax rate, and you'd like to see if any methods achieve that. So then for this, the minimax rate is actually known, and it's given here. So the SDP, if you compare that on the previous slide, is a little slower than this, but as Q goes towards 0, then SDP actually approaches the minimax rate. Okay, so you can compare to just the SDP-based recovery approach. The computational complexity now is given by this. Okay, so it's linear in the number of data points, but not too favorable in terms of the number of dimensions, versus a cheap diagonal thresholding method. You just sort of form the empirical covariance matrix, you rank order the diagonal elements, and that's it. That's how you get your support. And so you like to, if you got the same statistical efficiency here and here, you definitely always do this. But the question is, maybe you get better statistical efficiency here. You need fewer data points. You can afford the more computation. Okay, and so again, this same paper by Amini and Wainwright established a rescaled sample size for diagonal thresholding. It turned out to be n over the log of p. Again, that's very good. We're getting high dimensional results here, divided by k squared, where k is it's a hard thresholding model. It's the number of non-zero coefficients. Okay, so that's great. Do we get a better result for the SDP? So there's an empirical showing that in fact is the right answer. Everything lines up when you rescale in that way. And so if you do this now for the SDP, you get this thing here. It's divided by k. So that's much better. Okay? So instead of k squared, you're dividing by k. So you're getting a faster rate for the SDP than for the diagonal threshold. And this is now the same kind of empirical result for the SDP. Okay, so I think that's it. Yeah, that's it. So this is kind of a summary, is that back in the, so for multivariate regression, if you use a second order cone problem, it's a little more computationally complex, but you get better statistical results than using a quadratic program which is just the lasso. And then you can compare for sparse PCA two computational procedures, and you can also get rates, statistical rates for these as well. And I think I won't get into this, but there are notions of optimality, and you can try to see what's the best you can do in principle using information theoretic ideas. Okay, so the main kind of message there was kind of about rates and how you can also ask for rates not just in our classical asymptotics where the number of parameters is staying fixed and n is going to infinity, but you can let p and n go to infinity together. And many, many machine learning algorithms have that character, and the kind of tools being used here are applicable extremely broadly. They're not that hard. These, if you can look at the proofs here, these are not that hard to do. It's in fact, no empirical process theory is needed. It's just sort of asymptotics, but done kind of in a clean way. Sort of the SDP literature, complexity theorists try to get computational lower bounds on the problem. Then you have an SDP relaxation of the problem, and you can ask, is that the best you can do, and what's the probability of getting the right answer, and so on and so forth. So there's a literature on that. I'd say it's probably not as complete as we would like it to be for our applications, but it's certainly ongoing work. Yeah?
You shed some more light on how the multivariate regression connects to finding graph structures and where it's going on.
Defining graph structures? Yeah, this is it's work by people mainly at CMU, Larry Wasserman, John Lafferty, Hua, and others. So they have a bunch of papers. I just mostly point you to them. I mean, it's just basically that, just take a Gaussian graphical model, okay? But let's assume it's sparse. Okay, and so it's a directed graph. All right, and so I'm going to look at every node, and I'm going to look at all the other nodes as the covariates, so completely observed data. Okay, and so now it just becomes a linear regression at that node. Okay, but it's sparse linear regression. So apply the lasso, and then try to show that you do this uniformly over the graph in some sense. Or you can do things like this L1, L2 kind of penalty. You can say that the coefficients are also related. The regression here and here are related. The same components are relevant across multiple regressions.
The regression is happening on the conditional?
The what, sorry?
The regression is happening on the conditional?
They're on the conditionals. It's regressions at each node. So it's kind of a very simple idea, technology, but simple is often good. These graphical models, it's really hard to write down a marginal likelihood and go uphill in it, and it just runs really aground. So it might be a good idea in really large graphical models to do something extremely simple, try to prove something about it so you're not doing something ridiculous, and then do this on various problems. So it's a good developing literature. And there has been this literature on graphical model selection. But there's lots of kind of toy examples of it and precious few real life applications of it, and successful examples of algorithms that scale to real life scale problems. So this is kind of now let's do it in a different way and see if we can get closer to reality. Yeah?
So can you name one of these real life examples, applications, where it's really worth doing such a multivariate regression instead of just using lasso on the separate lines?
This paper is all theory, so we personally haven't been looking at the. Multivariate regression is a huge field in which there are there's tons of applications of it, and it is clearly of benefit to do multivariate regression compared to regression. I don't have lists of applications in my head, but there's a big literature on it for a good reason. So we just have made a theoretical contribution here. I don't know, but I can speculate. There are tons of biology examples where I can think I can clearly think it's appropriate, but we're going to follow it up with more problem oriented stuff. We did this in a NIST data set, and we showed that it was better and so on. That doesn't mean that much to me, but I guess it was kind of an interesting NIST data set in which we had a very few number of examples of each of the digits, and it was better than doing independent regressions. Finding the right features for each of the classifications was better than doing it separately. But I'll leave it to your creativity to think of problems. I mean, I think it's not hard to think of joint feature selection problems. You want to do feature selection, and you want to borrow strength across multiple feature selection problems. I just can't believe that's not a widely applicable idea. Okay, let's take a really short break, just a minute to stand up and stretch if you don't mind, because I would like to finish a little chunk of the last part of my talk. Okay, so I will beg your indulgence. It's the last talk, and it's the last part, and the lunch is about to happen and all that. So again, I'll kind of try to skip a little bit quickly here, but I think this will be of interest to many of you. This has to do with independence and conditional independence. And I think especially, I guess, Phil's in the audience somewhere. Y'all, Phil's in the audience. This is a very deep topic, and which people like Phil have contributed a great deal. And this is kind of a conditional independence story that I think is kind of interesting. So it'll relate to a lot of what you've learned during the past 2 weeks and other talks. The other reason I bring this up at this point is that again, it's going to be an algorithm that does something, and we want to give an analysis of it. And this is probably the hardest example. So this is a real kind of kernel methods hard problem. The algorithm machinery is not the second order cone problem or the SDP, which is somehow simpler to analyze. This is hard, and so we really need a real serious tool here. So we use empirical process theory and get good results. In this case, just consistency. But I'm kind of give you a hint of how that kind of harder argument goes and why we wanted to face it, because independence is a very important concept, basically. Okay, so this is joint work with Kenji Fukumizu and Francis Bach. Okay, so let me just kind of skip kind of quickly a little bit. So this is a topic that has mainly existed in the stat literature, mainly in the annals of statistics, and it's kind of surprising that machine learning people haven't also worked on it. Some people may have. You see more and more of this kind of thing, but it's basically regression where you have XY pairs and the covariate is high dimensional, and you want to find a projection of that high dimensional covariate onto a subspace S, just like you would do in PCA, but it's one that you take into account the response. So PCA doesn't take into account the response. Okay? So like discriminant analysis is an example of this classically for classification, where you're trying to find a subspace that allows you to do good separation. This is the regression version of that, and it's meant to be non-parametric. So we're going to do this. Well, the buzzword is semi-parametrically, i.e. the regression of y on x is allowed to be arbitrary, i.e. non-parametric. And we want to estimate, now we'll call it a parameter S. It's the subspace. It's a finite dimensional object, so it's really a parameter. And I want to estimate that under any arbitrary regression of y on x. Okay, so that is the problem. It's called semi-parametric because we have a non-parametric component, which is really a nuisance parameter for this problem. I'm not trying to estimate the regression. I'm just trying to get S. So S is the parameter. We have a non-parametric nuisance parameter. That's usually called semi-parametric problem. Okay, so the main, let me just jump to here. The main approach to this literature, which is called sufficient dimension reduction, trying to find this subspace S, has done it by inverse regression. So it turns the problem around. Says instead of trying to go from X to Y, where X is really high dimensional and Y is low dimensional, turn it around. Y might be one dimensional, and go from Y to X. Okay, so if Y is one dimensional, you go from Y to X. That's just a curve in the X space. Okay, so you could think about estimating that, and then maybe doing a PCA or something, finding the subspace in which that curve lies, and then turning it around and saying, well, that's the curve in which the data are aligned that are relevant to Y. Because I was able to do a regression from Y to X, therefore there's kind of a relationship, and maybe I'll recover a reasonable subspace there. So that's kind of an intuition, and that's been done. But to do this, to do an inverse regression from Y into X, now X is acting as the response, and in regression you have to put probabilistic assumptions on the response. You don't put it on the covariate, you put it on the response. And so to do this, we now need probabilistic assumptions on the covariate, which is what we're always trying to avoid in regression. So it just never felt right to me as kind of as a methodology. Right, but there's a big literature on it, and it is used. There are, it's practical applications of this, definitely. Lots of kind of graphical approaches to regression use this. So a little bit more formally, here's our regression. Y is the response. We have an n-dimensional covariate. And the goal is to find what's called the central subspace. And it's just defined by saying, well, I suppose I could write the regression as just a probability distribution of y given a projection of x onto some matrix B. Okay? So I'm going to project onto B. Let's just draw that right here. Maybe one-dimensional. So here's my x. I project onto B, and I get this B transpose x here. And maybe once I know that, I can predict y just as well as if I'd used x itself. So I have a conditional independence of x and y conditioning on B transpose x. Okay? So if I can find such a B, then I've kind of managed to project and not lose any information. Okay, so that's what's defined to be the central subspace, is this matrix B. It's the subspace defined by projection B. So here would be a little example of that. If you had logistic regression in x1, x2 coordinate, it looked like that. All right, then if you were to just look at the x1 coordinate, project into the x1 coordinate, you would get a perfectly good regression, and you would have lost any information. If you were to project in the x2 coordinate, you've lost information. So it's clear you'd want to choose the central subspace to be the x1 axis here. All right, in PCA, of course, if you just project, look at this data in the x1, x2 space, the PCA principal axis may have nothing to do with x1. It just depends on the variance of scale, which is unrelated to x1. Okay, so there's tons of methods. They're all interesting. I like contour regression in particular. There's a whole bunch of very clever ideas going on here. In a longer talk, I would get into these a little bit. Let me just tell you that they're all interesting and clever, and this is all published in the annals. There's all theory for all of these. So under certain assumptions, these all work. Okay, the assumptions are too strong, however, as I'll get into in a minute. Either as a linear assumption or an additive assumption, or most painfully, an elliptic assumption on the distribution of x. This is a very common assumption that's imposed. And that just doesn't feel right to me. I don't imagine elliptical data arise all that often in the x space, not for regression. Okay, so we'd like to get out of that kind of web of assumptions. All right, so let's now be really clear on how this relates to conditional independence. All right, so remember B is our projection matrix. So we take Bx. Let's fill that out. Let's take the orthogonal complement of that. C has columns orthogonal to B. And then define U to be the good stuff, the projection, and what we want to retain, and then V to be everything else. Okay, so the statement that B gives the projector on the central subspace is equivalent to saying that the conditional distribution of y given x is the same as the probability of y given B transpose x. That's the definition. All right, and that's the same as saying that this conditional distribution of y given both components, u and v, allow you to reconstruct x. So this is the same as saying this, because u is equal to B transpose x, for all y, u, and v. And that's just a way to express conditional independence of y and v given the projection onto u. Okay? All right, so that's, if you wanted to find the matrix B that does this, it's equivalent to find the matrix B that achieves conditional independence. Okay, so now all you got to do is find a way to express conditional independence as an objective function that you can go downhill in terms of B. So how do you express conditional independence as an objective function? That was our task that we set out to try to solve in this line of work. Okay. All right, so we did this using a non-parametric tools. So this kind of went back to, we learned about reproducing kernel Hilbert spaces by the work of many other people. I think you had a talk on this. And we noticed that this was basically just a way to get basis functions and then computationally efficient use of basis functions. We thought, well, maybe there's some richer uses of these spaces. We can maybe express operators on these spaces and look at those class of operators and see if those are interesting, not just the functions in the space itself, but the operators. And maybe they can be used to lead us towards non-supervised methods. All right, so that's kind of what this talk really ended up, or this line of research ended up being. This started with something called kernel ICA, and then went in this other direction. Okay, so we're going to talk about conditional independence. We're going to use reproducing kernel Hilbert spaces to characterize both independence and conditional independence. And so we're going to actually end up to talk about these kind of things. To talk about independence, we need two reproducing kernel Hilbert spaces, one here and one here. So we have an original data space X and another data space Y, and they're going to map into corresponding reproducing kernel Hilbert spaces. And then we'll talk about the relation among data points, pairs of data in these two spaces here. Okay, so you already had a talk on RKSHs. I won't belabor this. The main thing about RKSH, you have this kernel function, and the kernel has two arguments. And if you fix the second argument, and now this is now a function of the first argument, that is an object that lies in the reproducible kernel Hilbert space. And then when you inner product that with another function in the space, you just get evaluation. So that's called the reproducing property. I hope you've seen that somewhere else. Okay, and so now if you take inner products of, so phi is this mapping of, you take a point x and you map it into the function that where the second argument of the kernel is pinned down. So that's called phi of x, that's the feature map, if you will. And if you now take inner products of phi for one data point and phi for another data point, that just amounts to kernel evaluation, and you can actually expand that in the basis functions given by the kernel evaluated at particular points. Okay, so that's just kind of basic kernel methods. And now we're going to not talk about the kind of the points in the space, but the actual operators on the reproducing kernel Hilbert space. Okay, the operators. All right, so the way you do this is we're just going to find covariance operators, and so you look at random variables on the RKSH. You take that kernel function, and you pin down the second argument, but now treat that as random. And so we have a random function now for every choice of x. We get a different function. So it's a random function. Okay. And so now we can talk about covariance operators, which are give you it's like covariances on functions on function space. Okay. And so you define this in the usual way. You take an expectation of a product of the images of these things minus the product of the means. Okay, so now you have an operator which will operate on pairs of points from these two spaces and give you a number, an expectation. Okay, so there's the definition again, written up there. Just by using the properties of the RKSH, you get an actual kind of operator in the usual sense, which is that if you take a function in the RKSH, g, in the second RKSH, and you take a function f in the other RKSH, and you plug in this operator here, then you just get, by evaluation, you just get this object here, which is just the covariance of f of x and g of y. Okay? It's just a way of writing covariances of functionals of x and y. If I didn't have the f and g there, this would be the covariance of x and y. But now this is for arbitrary f and g. We get an operator that turns that into a single number for all f and all g. All right, so this looks very similar to kind of what you'd expect in the the Gaussian case. A covariance matrix is just this, and if you had linear combinations of x and y, you would get this kind of thing. And it's just really it's the nonlinear version of that. All right, so now with this, you can characterize independence, and this was our original work. What we did is that if you have a rich enough RKSH, basically using things like Gaussian kernels, then you get independence of x and y. That has nothing to do with the kernel spaces at all. You get that if and only if this operator is the zero operator. Okay, and I don't know, did Bernard talk about things related to this sort of thing? Bernard Scholkoff? A little bit. I think since I'm really nearly out of time, let me just sort of this is sitting here. It's a little easy calculation to do, and it's really not the focus, so let's just kind of leave it at that. It is easy to kind of understand this in terms of characteristic of functions. Characteristic functions factorize if and only if you have independence. And what we're really doing is replacing these kind of test functions with arbitrary entities in the RKSH. This would be kind of a Fourier, in Hilbert space characterization. We're working in a smaller Hilbert space, the RKSH. Okay. All right, so that's independence. What about conditional independence? Well, you can do conditional independence instead of working with covariance operators. You work with conditional covariance operators. All right, and so you define an operator in terms of these guys on the right-hand side are just operators that we've already defined, either on yx or xy or x with itself, and similarly with y. So you can plug in all these operators and define a new operator, and this new operator takes a function g and a function g, and gives you out this conditional variance, the expectation of that. So that looks, again, very much like what you'd expect in the Gaussian case. Okay, and so in particular for kind of our application, it's going to be, it's important to note that if x has two components to it, that when you condition only on one part of that, you get a covariance operator which is bigger in the sense of self-adjoint operators than the original covariance operator. So this kind of now starts to lead towards optimization principles. These operators can be ordered, and you can sort of talk about one being bigger than the other. You can start to get an optimization principle out of this. Okay, and so we have a theorem and I haven't really explained enough for you to really understand this, but I just want you to know that it exists, that this is a general characterization of conditional independence from the point of view of using these spaces. So if you have these sufficiently rich RKSHs, there's 3 of them now, which with kernels kx, ku, and ky, then conditional independence, which is a probabilistic notion, is completely independent, completely equivalent to the conditional covariance operators being the same. Okay? So if you reduce x just to the u and you didn't lose anything, we knew in general we had an inequality, but if you got an equality here, then that means you have conditional independence, if and only if. Yeah?
Does this hold for any characteristic kernel?
No, there is for universal kernels. Yeah, this has to be for rich enough for Hilbert spaces. Obviously, this wouldn't hold for... So for example, consider the Hilbert space of polynomial functions. You just get moments. And we know a finite set of moments aren't enough to characterize anything. But if you get an infinite set of moments, like in a rich RKSH, then you can get a characterization. And so you don't want to go all the way to all the moments that you would get in the expansion of e to the I omega x. That's too many of them. That's the full Hilbert space. So you go to these RKSHs, which are somehow smaller, easier to work with, but rich enough. That was kind of the discovery here, which is that you could get this characterization without going all the way out to characteristic functions, which might be too much. You can't really estimate them from data. Okay, so with that theorem, we now have a characterization of conditional independence. Sufficient dimension reduction means that we try to achieve conditional independence. We now have some operators that we could estimate from data, optimize them with respect to our matrix B, and if we get 0, we've got a conditional independence. We've discovered the central subspace. All right, so that's kind of quick, and I think I'm going to now be able to skip some slides because I'm nearly done. Kernel dimension reduction just means do what I just said. Estimate those operators from data, optimize them with respect to the B matrix, and go downhill until you get a good B matrix according to this metric. Okay, so I think I'm just going to skip some slides. We had this again. That equation was up there earlier, where this is now was called U before. It's now called B transpose X. So I want to be clear what we're trying to estimate is B, and our objective function is now we have this self-adjoint ordering, and we need to turn that into a numerical ordering. And so the trace is one way to do that. Okay, so we can optimize the trace of these operators over these matrices, which are projection matrices. That's called a Stiefel manifold. So there's now a very clean little optimization problem we can solve. And we now get the empirical versions of these. Let me just skip this page altogether, plug that in, and do a little bit of math. And now our optimization problem in terms of the data, these are now gram matrices, regularized. In terms of the data, becomes the minimization of a trace over this Stiefel manifold. So it's not a convex problem, it's a hard problem, it's hard to get theoretical handhold on, but you can write it down, you can solve it, and it's a new methodology for this problem. It makes no assumptions on the ellipticity of the data or any of those other classical assumptions. It's a much broader method. Okay, so the question then is that, does it work, first of all? And here's some comparisons of it. Finding a good subspace for particular data sets and comparing to a bunch of the existing methods. And of course, the whole point is here that it should be a better subspace for capturing the regression. This is, in fact, a classification, but we treated it using generalized linear models. And so we did this on various problems. And I think I'm done, basically, because all I wanted to do was now to say, can we do some theory of this thing? This is a pretty complicated operator to talk about, and so on. And so we can't just do kind of simple asymptotics around things. We have to do some global thing to do theory. All right, so now you pick up a book on empirical process theory, you learn about how to do that, and you apply those tools, in this particular case, in a Hilbert space. So if you're interested, we have a paper on this. You can look at how that's done, and you can now prove a theorem which says that this works, basically. That if you use a kernel which has some nice properties, if you choose the regularization parameters in the right ways, that the probability that your estimate it lies in a set that covers the correct answer, basically, goes to 1 and then goes to 3. So this is just basically a consistency result for this procedure. Okay, so I'm giving you no hint about how it's achieved. There's a lemma I think I'm going to skip entirely. And let me go back to that slide in a second. So that was my concluding slide. Okay, so empirical process theory. A couple of people asked me last time. I'd given a couple of examples of books. I mentioned one that I want to now write up, which is van der Waart has a very nice book on asymptotic statistics. I teach out of this. It's a bit of a challenge to teach out of and for the students to learn out of it. But by the end of the semester, Everyone seems to have gotten something out of it. It has a lot of empirical process theory in it. It has a lot of M estimation, a lot of asymptotics, a lot of asymptotic normality. It's got some Bayesian ideas in it, like Bernstein-von Mises theorems, and so on and so forth. And so I think anyone really serious about this field over the long term as a career, that kind of material you need to master. It should, you work your way up to it, but you should know how to use these tools. There's things like U statistics would allow you to not have independence. There's just all kinds of cool ideas that are available to you. Okay, so moreover, if you open that, you'll find a ton of a great bibliography and references to all kinds of other books and topics. So we basically kind of learn material out of this and various other books, and we're able to do this sort of work. Okay, so I'm done. Let me just now go back to my question. How many of you are Bayesians? Okay. All right. How many are frequentists? I got like 2 last time, so I got still 2 or 3. And how many are both? Okay, that's the right answer. So, I mean, if I really had to sort of only pick one, I would pick probably the Bayesian one. I think that is kind of, it protects you and against doing stupid things more gracefully. It is expressive. It's fun to work on, and so on. But I really don't want to feel constrained by that. I really think there are tons of interesting methods that we can develop with cleverness and thought and so on, and then you can say something about how they work. And then I also want to be not just coherent, I want to be calibrated. And so a lot of people have kind of hovered around the Bayesian and frequentist boundary. I can think about Larry Wasserman and Jim Berger and all, who've been concerned about these issues a lot, are worried about calibration, coherence, and these sort of things. And so it really is important to avail yourself of both ways of thinking about statistics. My own answer is really both, but it kind of also depends on the problem. If I'm working with a domain expert over a long period of time, I tend to be more Bayesian, because I really want to try to assess things and get them implicit and understand and so on. That tends to be a Bayesian kind of thing to do. If I'm working on a problem fairly quickly or writing a piece of software that someone will use out there, I want to be frequentist. I really want to give guarantees that my L1, L2 regression thing that you're going to use on tons of problems has frequentist guarantees. It will work with high probability on the data. Okay. So I view them as complementary. It's a unity of statistics. It's decision theoretic statistics. They're unified and very useful with each other, but it's not, I'm uncomfortable at times. And it's fun to kind of aim arrows at the 2 perspectives from one perspective to the other and sort of see where they break and so on. All right, but the main conclusion is that I hope that you believe this already, but now you believe it even more, that machine learning really is a part of statistics. It's this big problem of inference, statistical inference under uncertain, getting knowledge under uncertain situations and making decisions that are good despite your uncertainty. That's a big problem that we won't solve in our lifetimes. It's been around for hundreds of years. It will still be around. It's a great problem to be working on, and it's a huge field. If you ally yourself with all the other people out there working on it, it's really fun to get all the different perspectives. And so I would encourage you to read not just the machine learning literature, the latest NIPS and ICML papers, but read the statistical literature broadly, the books and all the journals. Places like Statistical Science are a great place to read. There's lots of kind of nicely written entree kind of articles there. You can learn a lot. A lot of us in machine learning have kind of rediscovered wheels, and it's been kind of interesting. You discover a cool new idea, you find it already existed in statistics. Oh boy. But then you get to read all these great papers and learn something useful that you can use on some other problem. So you guys are all young and have a lot of time on your hands. Read and ponder the literature and then contribute to it. Try to send your papers to stat journals and see what happens. Okay, thank you.